So last thing we're going to look at this week is how we can solve higher order, which just means inequalities that are quadratic or cubic, okay, not necessarily linear. How can we solve these by hand? And I'll also show you possibly a way we could also do it on the calculator. So we're going to look at an inequality involving a formula we've done before. Okay, this is the projectile motion formula. Negative 16t squared plus v sub 0 t plus s sub 0. So in there, the variable t stands for time. V sub 0 is initial velocity, or how fast the object was thrown or launched when it started. S sub 0 is our initial height. And if you plug in the t, v sub 0, and s sub 0 into this formula, you can calculate how high your object is at any time. All right, so we're going to start out with a problem where we use the graphing calculator to find the answer, and then I'll show you guys how we can do a little bit different method to find the answer. Does everybody have the projectile motion formula? So this one says that we're going to throw a ball straight up from ground level with an initial velocity of 80 feet per second. So let's fill in our formula first, and then we'll go from there. So S equals, and what comes right on the other side of the equal sign? This would never change, no matter what problem, what the initial data is. Yep?
Negative 16.
Yep, negative 16, and what comes after that? T squared. So that's always your first term, negative 16t squared, plus v sub 0 t. What's v sub 0 in this case? Francesca?
80.
80. T plus s sub 0. S sub 0 is the initial height. Matt, what's my initial height here? Well, what does it tell us the starting height of the ball is?
Ground level.
Ground level.
So 0.
0. So we don't even have to put plus 0. So there's my equation that represents the height. Now the question is this. When is the height greater than or equal to 64? Remember, that's what at least means. Like if you said to me, I have to get at least a 90 on the test. At least a 90 means 90 or higher. So at least 64 feet is 64 feet or higher. So that's your height because it's equal to S. S is height. So we want the height to be greater than or equal to 64. So plug that in, and then we'll have the setup that we're going to do on the calculator. So we've got negative 16t squared plus 80t is greater than or equal to 64. All right, so Abigail, where do you think I'm going to plug in the negative 16t squared plus 80t?
Sorry.
Where do you think we're going to plug in the left-hand side?
Into the y equals.
Which one?
First one.
Yeah, we'll just put that in y1. All right, so put in negative 16 Remember, you have to use x as your variable. Plus 80x. All right, we got that. And Jack, where do you think we're going to plug in the 64?
Y2.
Yep, we'll put that in y2. Let's take a look at our window. Okay, x is time. Casey, what's the lowest value we could have for time? 0. Yeah, we can't have negative time. What's the maximum time? Well, it depends on how long the object is in the air. We don't know that. So we'll leave that at 10. Y is the height. So Ethan, what's the lowest that this object would ever be?
0.
0. And the highest, we don't know. Let's try like 120 feet. If it goes off the screen, we're going to have to just set it a little higher. But let's try that window. Hit graph. Perfect. So that represents the ball being thrown. That represents a line at 64 feet. Now, what do you think I'm going to have to calculate in that picture? Yep, go ahead, Zach.
The intersection.
Yeah, I need the intersection. Because in this green section is when the ball is above the red line, or equal. That's 64 feet. So I want to know, when does it go above that? And when does it go above that? So we have to find those two time values. So let's do second, calc, intersect, blue, red, and I'm going to do the one on the left first. That should be close enough. It says x equals 1. And the other intersection point, you can check it, but it does come out to 4. So that means between 1 second and 4 seconds, this object will be above 64 feet. Before 1 second, it's still on its way up. After 4 seconds, it's already come back down below 64. And that's one way you can solve an inequality using the calculator. Okay, any question on that? Okay. So next thing I want to look at is how long does the ball stay in the air? What do we know about the height of the ball if it's in the air? Yeah, Chris?
It's greater than 0.
It's greater than 0. So this time I don't want height greater than 64. I just want height greater than 0. So my height is negative 16t squared plus 80t. And I want that greater than 0. Now, this is a quadratic, but we don't have to get anything fancy to solve it because it doesn't have a constant. Whenever you only have the squared and the linear term, you can factor out usually what they have in common and then solve. So what do both of these terms have in common that we could factor out? Ted?
T.
Yep, they have a t. Is there anything else that they have that we could factor out?
A 4.
We can go even more than a 4. Yeah?
16.
16, and I'm even going to factor the negative out with it. Okay, so let's factor out a negative 16t. If you factor out negative 16t from this, what would you be left with? Think about what you would multiply this by to get that back. Yeah, Jake?
Would it just be T?
Just be t. And then we know it's going to be a minus, because a minus times a minus is a plus. And what would you have here? Negative 16t times what is 80t? Yep. Yep. Negative 5. So we factored out the negative 16t. Now, the next step, we've done this kind of thinking before in a homework problem. We have something times something, and it's greater than 0. How can you multiply two things together and get an answer that's greater than 0? If you had what kind of number times what kind of number? Tyler?
A positive, or negative, negative.
So you either have to multiply a positive times a positive, and you will get an answer greater than 0, or a negative times a negative is also greater than 0. Only one of these is possible here. The other one is impossible. Look at this first factor. Negative 16t. That one in red is like this column. It's the first one. What kind of number is time in our problem? Time will always be, Jake? Time is always going to be a positive number. So you're going to take an always positive number and multiply it by negative 16. What kind of result am I always going to get in the red box? Yep.
Negative number?
I'm always going to get a negative number in that red box. Say time is 2. 2 times negative 16 is negative 32. So time is always positive times a number that's always negative. You're always going to get a negative result. That means in order for what's in the red box to be multiplied by what's in the black box and get a positive result, what's in the black box has to also be negative. So if this is always negative, then this has to be negative to get a result that's greater than 0. Any question on that? So really, the question now is just when is t minus 5 a negative number? That's what we have to find out. When is t minus 5 negative? Negative means below 0. When is it less than 0? So add 5 to both sides. That tells you how long the object is in the air for. Can somebody interpret what that means? T is less than 5. So how long is the ball in the air? Jake?
Less than 5 seconds.
Just less than 5 seconds, like 4.9. At 5 seconds, it's back on the ground. But just under 5 seconds, like 4.99999, that's how long it's in the air for. So just less than 5. And that's the answer. Right? So we were able to do that one algebraically. Okay, we didn't have to graph anything to do that one. And when we want to solve inequalities without graphing them, in general, we can use what's called a sine pattern. Now, what a sine pattern is it's when you make a number line and you mark part of the number line as positive results and the other part of the number line is negative results, depending on a formula you're plugging into. This whole method relies on you having an inequality that you can factor. Right? If you can't factor it, either because you don't know how to factor it or because it's impossible to factor it, then this method's not going to work. Okay, so this method only applies to problems you can factor. And when you factor something, you might end up with something like that. T minus 1. That's a linear factor because the exponent on the variable is a 1. We're not talking about having like something like that. Right? T plus 4, that's another linear factor. X plus 6, x minus 12. Right? A letter plus or minus a number. That's a linear factor. And anytime you write a factor like that, there's exactly one number you can plug in that would make it 0. Can anybody tell me for the top one what number you would plug in for t to make that 0? Yeah? Positive 1. And what would you plug into the bottom one to make that 0? Francesca?
-4.
-4. So the idea is we're going to draw a number line for each linear factor. I'll do the bottom one. It would look something like this. Here's my number line. You're going to mark the 0. In this case, it's at -4. Now, I have two sections on my number line. I have a section to the left of -4. I have a section to the right. Let's see what happens if we plug in a number bigger than -4. You could pick them if you want to try it. Try 0. Anything bigger than -4. If you pick a number bigger than -4 and fill it into what I just circled, what kind of answer do you get? Positive or negative? Yeah, you get a positive. Now, pick a number that's below -4. -10. Anything below -4. If you fill it into what's circled, what kind of answer do you get now? You get a negative. So we drew a number line. We marked the number that gave us exactly 0. And then anything to the right of that will give you a positive. Any number below that will result in a negative. That's called a sine pattern. Any question on that? All right. So, however much room it took you to write that step, leave the same amount of space, because there's one more step. But I want to start a problem and just get to this point. And then I'll give you the last step. So just leave a couple lines. And we're going to do an example. And I'll come back to that. So, let's see if we can solve this one. So the first step is you have to factor it. You have to be able to factor it. Again, there's all kinds of different methods to factor. We're not really learning the methods here. All I care about is that you can factor it somehow. What would be my first term in each set of parentheses? Anybody tell me what would go in each one? Chris?
2x and x.
Good. 2x and x. How about my signs? What do my signs have to be in parentheses? Tyler?
Positive and a negative.
Yep, positive and a negative. I would do it this way because that's the answer. So we'll do it that way. And now I need two numbers that multiply to give me 5. How about Ethan? Can you give me two numbers?
To equal 5.
Yeah.
5 and 1.
5 and 1. I'll do 5 and 1. Let's check it. 2x squared, good. 2x times 5 is 10x. Negative 1 times x is negative x. 10 take away 1 is 9. Perfect. So we factored it correctly. Any question on the factor? All right. Now that we factored it, we're going to make a number line for each factor. And the first thing we want to do is mark the number that would plug in and give us 0. All right. So how about Sarah? Can you tell me what I would plug in for x in 2x minus 1 so that I get 0? What did you say?
1.
Let's try it. What's 2 times 1? 2 minus 1? 1. So that plugging in 1 here didn't give me 0. It's got to be less than 1.
0.
What's 2 times 0?
0.
0, take away 1?
Negative.
-1. So it's between 0 and 1. Yep, 1/2. Okay, so let's mark the root there. And let's do the root here too. Matt, what would you plug into the second factor to make that 0?
-5.
-5. These are two totally separate number lines. They're not to scale with each other. They're totally separate. All right, so we got -5. Abigail, if I plug in numbers bigger than 1/2 into that, what kind of answer will I get? Positive. Okay, just pick a number bigger than 1/2. Pick 1. Plug it in for x and see what you get. You get a positive. All right, Jack, what if I plug in numbers smaller than 1/2?
Negative.
I'll get negatives. Okay. Try 0. 2 times 0 is 0, minus 1 is -1. We just said that.
I apologize for the interruption.
All right, so Casey, what about this one? If I plug in a number bigger than -5, what kind of result will I get there? Positive. All right. And Chris, if I plug in a number smaller than -5, what kind of result do I get?
Negative number.
Negative, yep. All right, so there's our sine pattern for each factor. Now, the last step is once we have a sine pattern for the individual terms, which we just did, combine them together to look at the result for the final answer. In our particular case, we're going to be examining a product, something times something. Okay, so we're going to be examining a product. So when we combine them into one number line, what you're going to do is mark both roots on the same number line. So you're going to mark the 1/2, and you're going to put a mark at -5. Okay, we'll mark both. Here is the number line that's going to represent both of these combined together. Put a mark at -5. Put a mark at 1/2. We just split the number line up into 3 sections. 1, 2, 3. We have to figure out the sign in each section. But we're going to figure that out using what we already have up above. The first section we're going to look at is this. Everything from -5 and below. If we look at the first number line, what section of the number line are you in if you are below -5? In the first number line. Yes, Jack?
Negative.
Negatives. Yep, you would be in the negatives. So you'd have a negative here. And now let's look at below -5 in the second number line. What section would you be in on the second number line? Okay,
Negative.
you'd be in negative again. So if you pick a number below -5, you'll get a negative result here. You'll get a negative result here. What's a negative times a negative? Positive. So that means in the original problem, numbers below -5 will result in a positive answer. All right, now, let's try this section. Between -5 and 1/2. Matt, if I'm between -5.5, what section of my first number line am I in? Yep, I'm in the negatives. Francesca, if I'm between -5.5, how about in the second number line?
Negative? Positive?
Positive, right? 1/2 would be like over here somewhere. So between -5.5, we'd be in the positive section. And Casey, what's a negative times a positive? Negative. So if you pick any number in section 2 and plug it into the original problem, you will get a negative result. And now let's look at the last section. Section 3 are the numbers greater than 1/2. So Zach, if I'm greater than 1/2, where would I be on the first number line?
Positive.
Positive. And Tyler, if I'm greater than 1/2, where would I be on the second number line?
Positive.
I'd be into the positive section. That would be a positive times a positive, which is a positive. So the original question is always either going to ask, where are you less than 0, which means negative, or where are you greater than 0, which means positive. Let's go back up to ours. Greater than 0. So we want to look on the number line at sections that are greater than 0. Which sections there are greater than 0? Yep, Sarah? 1 and 3. Those are unbounded intervals. Okay, unbounded. So let's start with section 1. How would we represent the numbers in section 1 as an interval? It's like everything that would be in that red graph. Yep, Zach?
Negative infinity. -5.
Yep, negative infinity up to not including -5. The reason it's not including, there's no equal to. If there was an equal to, I would put a bracket on -5. Or, how do we describe the other section where we are greater than 0, where we get positive results? Yeah, Chris?
Positive 1/2 to infinity.
And what kind of symbols on that?
It would be not including 1/2.
What about infinity?
Doesn't matter. It would be
So from 1/2 to infinity, open interval. Now if they asked, where are you less than 0? If they flip the sign around, then it would be the interval in green. The bounded interval between -5 and 1/2. Still parentheses though, because it doesn't have the equal to. But that's how you do what's called a sine pattern. Any question on that? Okay. So that whole method relies on being able to factor. If you get something that you can't factor, then we're just going to do it on the graphing calculator, pretty much like you did in last night's homework. You're going to graph two things and then find an intersect. Okay, so basically you can just shorten that to say if you can't factor it, use the graphing calculator. And we'll try this. I'm going to do this one using the method that we learned where you don't have to rearrange it. You just put something in y1, you put something in y2, and you see where one of them is above the other. We did learn another method yesterday where you get 0 on one side first. I'm not going to do that with this one. But you could. Okay. All right, so we've got, what is it? X cubed minus 2x squared put that in. And the color, the fact that it's in color, that really helps us here too. X cubed minus 2x squared minus 5x plus 7 minus 5x plus 7. So put that in y1. And then put the other side in y2. 2x plus 1. I'm going to try zoom 6 and see how it looks. Right, so my cubic function is in blue. It was this one. And I want to know where that one is above the red one. Okay, so here's my picture. First of all, is the blue one ever above the red one? What do you think, Ashley?
Yes.
Can you tell me how many different sections is the blue above the red?
3.
Okay. What do you think? What do we have to find first? I think we have to find here. Tyler?
The intersection?
Yeah, let's find the intersections. Okay, well, all 3 of those. So we've got second calc intersect. Let's just do 1, 2, 3 and see which one it gives me. Okay, that's the middle. 0.76, comma, 2.51. 0.76, comma, 2.51. Remember, we're interested in the x value. That's what we're solving for in this problem. So this y value, it doesn't mean anything. We don't need it. Okay, the 0.76 we need. This one. How about somebody else do the first one, and then I'll do the last one on the right. So second calc intersect. Blue, red. Now I need to move my guess. Should be good enough. 3.51, 8.02. Okay, and what's this last, or the first? Sarah?
Negative 2.26, negative 3.56.
And can you say the first part again? What 0.26?
Negative 2.
Negative 2.26, negative 3.56. Okay. So when I look at this, I see 2 sections where the blue is above the red. The 2 sections I see are from here to there. Okay, I see that section. And then I also see this section. Just barely can see it, but that other section will always be above the red. So the way we would describe where the blue is greater than or equal to the red would be when we are between negative 2.26 including, I have equal to, so I can include negative 2.26 up to 0.76. That's section 1. Or, I also have section 2. Section 2 is from 3.51 to infinity. Anything greater than a value of 3.51 to infinity. Again, bracket, because I can be equal to, but because I'm going to infinity, we always put a parenthesis because we can't include it. All right. Any question on that? And this was section 2. All right, so that's the end of 2.5. So any questions on that? So the last thing we'll take a look at, I think it's a little bit easier than 2.5, is 3.1. And that's on graphs of polynomial functions. So an example of what a polynomial could look like, something like this. That's an example. So the important thing is when we write polynomials, the exponents are non-negative integers. So we couldn't have an exponent like x to the negative 8th. We also couldn't have an exponent like x to the 2.5. Anytime you write a polynomial, the exponents are non-negative integers. The coefficients are real numbers. 2 is the coefficient in front of x squared. 2 is a real number. Negative 8 is a real number. What you couldn't have is something like this. 2ix squared. I is imaginary. No, can't have that. You could have a decimal. 2.3x squared, no problem with that at all. I didn't say you couldn't have a decimal in the coefficient. I said you couldn't have a decimal in the exponent. Now, let's see. The highest exponent is what we call the degree of the polynomial. So could anyone tell me, looking at the one I wrote in blue, what's the degree of that polynomial? Jake?
It would be 3.
Yeah, this is called a degree 3. We could also call that a cubic polynomial. Now, what if I did this? 0 times x cubed. What would be my degree now, Chris?
It would be the 2.
It would be the 2. When you multiply something by 0, you might as well just erase it. It's not even there anymore. So now the highest exponent is really a 2. So just make sure they didn't do something tricky and multiply by like a 0 in front. So as I said, a couple polynomials have special names. 1 is linear, 2 is quadratic, 3 is cubic. Beyond that, well, 4 is quartic, but really beyond that, we just say it's a polynomial of degree 5 or degree 6. No special name. Now, one thing that's nice about polynomials that's really easy is the domain. The domain is always all real numbers for every polynomial. The domain is all real numbers. The range, that depends. Right? Think of like if you had a parabola, and I asked you, what's the range? Well, in this case, it has a maximum value. And then from there, it goes down forever. What is the maximum value? Well, that's different in every parabola. Depends on the problem. But the domain is all real numbers. So cubic functions, I know we've looked at some of them before, but they kind of look like this. Usually they fall into one of these 4 basic types. One of them goes up on the right, the other one goes down on the right, and the other 2 take a turn in the middle. And the turn can be more or less pronounced. Like if you had something like this, that would still be the same basic type. But cubic polynomials generally look like that. And that's like the one I gave you an example of. I just filled in a number for A, B, C, and D. Fourth degree polynomials, they just add one more term. And you don't have to have every one of those terms. Here's the simplest fourth degree polynomial you could have. Doesn't have a cubic term, squared term, linear, or a constant. It's just y equals x to the fourth. That's it. But fourth degree polynomials can have one more term in them. Notice I didn't say have to. They could have one more term. So what you can end up with is something like that in the most complicated case. In the simplest case, like this one, you end up with something that looks kind of like a parabola. The difference is the bottom is a little flatter. If you were to graph this, it would look more like this. Doesn't quite really have what we call a vertex. At least I don't think they call it a vertex. It looks flatter. Not perfectly flat, but noticeably flatter. Let's try this one. Find the domain and the range. Well, first question should not require too much thought. What's the domain of that one? Yep. All real numbers. The only thing you're not allowed to do is take the square root of a negative. You're never going to have a square root in a polynomial. The other thing you can't do is divide by a variable that's 0. Well, you're never going to have a variable in the bottom of a fraction either. So, domain, all real numbers. Or if you like interval notation, just like that. Now, let's graph it. And that's going to help us find the range. So x to the fourth plus 5x cubed plus 2x squared minus 8x plus 1. I'll do zoom 6. I think we might have to adjust it. Yeah. We're close. We just got to set the y min a little bit lower. I would try maybe, try negative 15. It doesn't look like it's that much lower. You just want to be able to see the important things on the screen. Perfect. All right, so when we look at this graph, does this graph go up forever or down forever? Which one? Jack?
Up.
Yeah, it goes up forever. Does it go down forever? No. If it doesn't go down forever, then that means it stops going down somewhere. It stops going down right there. We need to find that point. When I press second calc, which option here do you think is going to help me find that point? Yeah, minimum. And minimum is just like calculating a root. Not sure if we've done it before, we might have. You pick a value that you know is to the left. You hit enter. Pick a value that you know is to the right. Hit enter. And now it looks like that. And the last thing they ask for is a guess. Hit enter. And it tells me two numbers. Where the minimum occurs and what the minimum is. So in this case, the range is everything from negative 11.94 up. So range, that's from negative 11.9, actually it would be 95, and up. Goes up forever. When they asked for the range, remember range, you always focus on the y value. Domain is the x. Any question on how we got that? So that point that we just found, where the W shape looks, I think it looks like that. That point right there is called a local minimum. It's called a local minimum. This point is called a local maximum. And when we say that something is a local min or max, it's kind of like saying you're a local champion. Right? We're not saying you're the champion of everybody in the world. You're the champion of your little area, locally, maybe in a city, or a state, local. So in this case, I'm not saying that that value is higher than everything else. I'm just saying that it's higher than everything else around it in a little area. Okay, so a local maximum is a point on the graph that is basically higher than everything around it. And a local minimum is a point on the graph that is lower than everything else around it. So a local minimum is a point on a graph that is lower than all other points around it in a certain area. And together, if I ask you on the test or in the homework to find the local extrema, that just means tell me all the local maxes and mins. So I'm not gonna do both a max and a min. Let's do one of them, just to make sure people understand the difference between what the maximum is versus where the maximum is. Okay, there's a difference between those two questions. All right, this says minimum. I'll do another minimum. It's the same thing. So, type in x cubed minus 4x. Big graph. This might not be a good window. It might be okay. That's fine. It says find the local minimum and then tell me where it occurs. So let's do second calc minimum. Left, right, guess. Which one of those numbers, the x or the y, is my local minimum? Yep, the y value. So when x equals 1.15, we get a minimum of negative 3.08. That's how you would answer that question. Where does the minimum occur? When x is 1.15. What is the minimum? Negative 3.08. And maximum is the same way. Second calc maximum. Pick left, pick right, do your guess. Okay, any question on that? So the last thing I'm going to show you, there's no question that I'm going to ask in the notes associated with it. It's more just something to think about. It involves looking at a graph like that and just telling me where it's increasing and where it's decreasing. And I want you to notice something. Anybody tell me on this graph, where is it increasing? From where to where? Where is it increasing? Yep.
From B to C.
Yeah, from B to C. We'll do it as an open interval, because when you're exactly at B, it's flat. It's not increasing or decreasing. So I think, yep, I agree with that. Increasing from B to C. Where is it decreasing? Jeff?
A to B.
Yep.
C to D.
I would agree. A to B. Or what's the other one you said?
C to D.
C to D. It's increasing. Now, the next question, what happens as a function goes from increasing to decreasing? What happens as a function goes from increasing to decreasing? I guess what ends up being created when a graph goes from increasing to decreasing? Casey? Can you be more specific about what's happening there besides just a curve? So the slope changes, and how could we connect that into what we just mentioned earlier, like on the last slide? Like, what is point C? That's where we go from increasing to decreasing. Yes. So when we go from increasing to decreasing, you get a local max. And what about when you go from decreasing to increasing? What do you get? Yep.
You get a local min.
Local min. Yeah. So again, there's not really a problem connected with that. I just want you to kind of understand what a local max and what a local min means. It's where a graph goes from increasing to decreasing, or vice versa. And then when you're exactly at a local max or min, like if you were standing right there, it would be perfectly flat. You wouldn't feel like you're uphill, you wouldn't feel like you're downhill. It's a flat spot. And the fact that it's a flat spot right there and right there, in calculus, we can use the fact that the slope there is perfectly flat to figure out mins and maxes without a calculator. Just involves the fact that the slope is 0 at that spot. Okay, but we do it with the graphing calculator. Okay, any questions on all that? So I think I'm probably going to have enough time for me to put up the topics on the test. I just have to take a quick look at it. But let me put up homework. So page 116. Maybe 9 or 10 questions from there, and then another 9 or I think 9 or so questions from page 149. We'll take a look at those tomorrow, and then the plan will be after that to do the test. Okay, so topics you'll see on the test tomorrow include solving linear and quadratic equations, solving linear and absolute value inequalities, solving quadratic inequalities, that's using the Sine Pattern, calculating intersects on the graphing calculator to solve an inequality, using the graphing calculator to find maxes and mins, and using the calculator to find domain and range.